Last class, successfully we completed kinetic theory of gases. Particularly in gaseous state, kinetic theory of gases, this concept is very important for JEE mains and JEE advanced. Even for public exam, they ask 4 marks question from kinetic theory of gases, particularly postulates, and different types of velocities, RMS velocity, average velocity, most probable velocity definitions, particularly 2 marks question, and their equations and relation between RMS velocity, average velocity, and most probable velocity, and total kinetic energy, average kinetic energy, derivation of Boyle's law, Charles law, Gay-Lussac law, and Graham law of diffusion from kinetic theory of gases. So these are very, very important concepts for the competitive exams. Okay, students, have you solved that question? I have given one question in yesterday class. Did you solve that question? Neha, very good. Remaining students? Remaining students. Okay. Kartikeya, okay, Nana, very good. So question is, calculate the pressure in Pascal exerted by how many particles? 10 to the power of 23 particles. And each particle mass 10 to the power of minus 22 grams. Volume 1 decimeter cube. RMS velocity 10 to the power of 5 centimeter per second. So these are the given values. According to kinetic gas equation, PV equal to 1 by 3 mn c square, where P is the pressure of the gas, V is the volume of the gas, m mass of each gas particle, n number of gas particles, c RMS velocity. Question, pressure in pascals. Students, Pascal means Newton by meter square. Am I correct? What is Newton? Newton is kilogram meter second inverse 2. And this is Pascal. Kilogram meter second inverse 2 by meter square. Meter square cancel. Now Pascal means kilogram meter inverse second inverse 2. So you have to get the value in kilogram, in meter inverse, in second inverse 2. Okay, fine. So P equal to 1 by 3 mn c square by V. So this is the required equation. 1 by 3 mass should be kilogram, but it is given in grams. Convert into kilogram, 10 to the power of minus 25 kilogram. Number of gas particles, 10 to the power of 23. And c square, RMS velocity, 10 to the power of 5 centimeter, but we need meters. 1 centimeter equal to 10 to the power of minus 2. So it will be 10 cube meter per second whole square. Because 10 to the power of 5 into 10 to the power of minus 2, 10 to the power of 3 by 1 decimeter cube volume. It should be meter cube. 1 decimeter cube means 1 liter. 1 liter means how many meter cube? 10 to the power of minus 3 into meter cube. So By solving all these values, students, answer is 3.33 into 10 to the power of 6 pascals. Understood? So you have to do question based on the units. So units also very important, students. Neha, did you get same answer? No. Okay. Okay. Fine. Very good. Okay. Next question is, at what temperature will be the total kinetic energy of 0.8 moles of helium gas be the same total kinetic energy of 0.4 moles of argon gas at 400 Kelvin. Vikrant. Okay, Vikrant. Well try. Aditya, okay. Kartikeya, okay. Yes, very good, all of you. Question: at what temperature will be the total kinetic energy of 0.8 moles of helium gas be the same total kinetic energy of 0.5 moles of argon gas at 400 Kelvin? And we know that total kinetic energy formula. I have given total kinetic energy formula 3 by 2 RT. This is for 1 mole. For n moles, nRT. If n value 1, 3 by 2 RT. For n moles, 3 by 2 nRT. Kinetic energy of helium gas, kinetic energy of argon gas, both are same. So 3 by 2 number of moles of helium RT, temperature of helium, equal to 3 by 2 number of moles of argon or temperature of argon. So obviously 3 by 2 get cancelled. R cancel. And the number of moles of helium 0.8. Temperature we don't know. Number of moles of argon 0.4. Temperature 400 Kelvin. Then temperature of helium 0.4 into 400 by 0.8. 2 times cancel. Answer 200 Kelvin. Students understood? Very easy question. Calculate kinetic energy of kinetic energy in joules of 8 grams of methane at 27 degrees Celsius. Kartikeya. Okay, Kartikeya. Shashank. Okay. Jayant. Okay. Yes. Question: calculate kinetic energy. Kinetic energy means total kinetic energy, but specifically they ask average kinetic energy. In case if they want to ask average kinetic energy, they mention it is average kinetic energy. Otherwise, total kinetic energy, kinetic energy. Kinetic energy formula 3 by 2 nRT. Question: kinetic energy we have to calculate in joules. So R value in joules 8.314. I have given already. 3 by 2 N value 8 grams per 16 into 8.314. Temperature 27 degrees 300. Okay, students. And if you solve this, you will get 1875 joule per second. I think someone got this answer. So very easy question. Next, calculate average kinetic energy of 0.5 moles of ideal gas at 0 degrees Celsius. Joules only. Energy in joules always, not per joule per second. Jayant, okay. Shashank, very good, Nanna. Shashank. Shashank, very good. Okay. So question is average kinetic energy. Average kinetic energy formula 3 by 2 nkt, where k is Boltzmann constant. Where k is Boltzmann constant, not nrt. It is nkt. 3 by 2, number of moles of gas 0.5, k value 1.3 into 10 to the power minus 23, temperature 273 Kelvin. And by solving all this, you will get 5.6 into 10 to the power of minus 21 joules. So that is the difference between average kinetic energy and total kinetic energy. In case question average kinetic energy, formula 3 by 2 nkt. Total kinetic energy nRT. Yes, 3 by 2 nkt, average kinetic energy already explained. nkt, where k is Boltzmann constant. Okay. At what temperature will hydrogen molecules have the same RMS velocity as nitrogen at 27 degrees Celsius? Aditya, okay? Shashank, okay? Vikrant, okay? Okay, RMS velocity formula is root over 3 RT by M. So in question they said hydrogen molecules have same RMS velocity as nitrogen at 27 degrees centigrade. What is the temperature of the hydrogen? Okay, from this square root of 3 RT temperature of hydrogen by molecular mass of hydrogen 2 square root of 3R temperature of nitrogen 27 degrees centigrade. So 300 Kelvin. Always you have to take in Kelvin only by 28 because nitrogen molecular mass is 28. Squares cancel both sides. I mean roots cancel, then 3R cancel. Finally temperature of hydrogen by 2 equal to 300 by 28. 14 times cancel. Students, 300 by 14. What is the value? 300 by 14. So answer 21.4 Kelvin. So that is the answer, students. So do you understand how to solve questions in kinetic theory of gases? Very important, students, and very easy questions also. Yes, students completed. Okay. And next one is very, very important. Maxwell Boltzmann distribution curves. Who is that? Maxwell Boltzmann distribution curves. We know that in a container, any kind of container, whether it is cubic container or a cylindrical container, anything, irrespective of the gases, irrespective of the density of gases, whatever it may be, gases can move randomly at all the time. They will not settle down because they do not lose their energy. One molecule can move in one direction, another molecule in opposite direction. They may collide each other or the walls of the container. So one molecule, let's say this molecule, let us consider this molecule. Can you say exactly what is the velocity of this molecule? Definitely impossible. Why? This molecule velocity is not constant. The velocity frequently changes because it may collide with this molecule or walls of the container. Each and every second, in fraction of seconds, the velocity may increase or may decrease. So it is very difficult to identify the exact velocity of the molecule in a container or anywhere. Students Maxwell and Boltzmann, they studied the velocities of gas molecules with help of mathematics. They applied theory of probability. In 10th class, we studied probability chapter in mathematics. So same concept they applied for the gases. Theory of probability. So it is completely probability. If they consider 1000 gas molecules, in 1000 molecules, how they behaved in the container, like in 100 students in a class, how they behave in the class. Some students in front bench or middle bench, mostly they won't talk or they will study always. Some students who are still sitting in back bench, mostly they're going to be sleep or they won't listen the classes. They will chit chat always. Some students, most of the students, they are talking with other friends. Very few students only maybe uh, studying without, in case teacher is not there in the class. At the same kind of probability we are applying to the gases. In 100 gas molecules, some gases are moving in faster, some gases are moving in very slow, some gases middle, maybe they have equal velocities. Same kind of probability, same kind of application they apply to the gases. And the observed students, they have different equations, no need of that equation. uh, Definitely we require some equations to solve this type of probability equations. What they observed, in y axis, fraction of molecules, in x axis it is velocity or speed of the gas molecules. Let us consider 100 molecules. They observed the 100 molecules graph is, this is the 100 molecules graph at a T1 temperature. This is the graph. So this curve under this area, completely total number of gas molecule, let's say 100 gas molecules. So it is completely scientifical observed graph. I mean, a computer graph, simply by applying how we studied Schrodinger wave equation. Same in a same way they applied different equations. They got this kind of curve, some probability mathematics. With help of this graph, what we can understand, that is the point. So getting graph is not important. With help of this graph, what we can understand theoretically. Yes, what we can understand, fraction of molecules, if you observe at temperature T1, this area, this area, this area, very low fraction of molecules are present. Even this area also very low fraction of molecules are present. This particular velocity is low velocity, this particular velocity is high velocity. So they concluded that in a container at temperature T1, very low fraction of molecules are having lower velocities and higher velocities. So high velocity containing molecules, low velocity containing molecules are very, very low fraction. Okay. And when velocity of gas molecules increases, fraction of molecules also increasing. When it reaches to maximum fraction, this is the maximum fraction. This velocity. After that, velocity increases, fraction of molecules possessing that decreases. And they said this velocity is called most probable velocity. Why? Because most probable velocity is what? The maximum molecule possessing velocity. This is the maximum fraction. This fraction of molecules possessing velocity is what? Most probable velocity. Okay, students. I can explain how they constructed this graph. Very simple way I will explain with the students. In a class, 100 students are there. If I apply theory of probability for the 100 students without teacher, in 100 students, generally, in all the cases, it may be not correct. General observation, front bench students without teacher, maybe they will try to study. They will try to study, or they will sleep, or they will try to take rest at that point. Okay. Backbench students also, mostly they will sleep or they will try to take rest. Okay. Some students, most of the students in middle bench students and general observation students, most of the students, either they chit chat with other students or they will fight with other students or something going on between most of the students. So if you apply graph theory of probability, like fraction of students who are studying, like, so some students are, most of the, I mean, very few students are having focus on studies. Okay. And very few students are having lack of focus of studies. Some students are, very few fraction of students have very good focus on studies. And most of these students under this curve. So this is simply theory of probability. And one point from this, if you increase the temperature, what will happen? If temperature increases, students, they got very interesting graph. The graph is, so this is the graph when temperature increases. This is T2, where T2 is greater than T1. So from this graph, what we can understand, see, this fraction of molecules and this fraction of molecules. If you observe, when temperature increases, maximum velocity possessing molecules are increased. Here very low fraction, here fraction of molecules increases. When temperature increases, very low fraction of molecule, very low velocity possessing fraction of molecules are very low. I mean, low velocity molecules are now very low. And the flat here, this is the peak of the curve. Exactly, we can see the peak of the curve. This under this peak, this is the fraction of molecules. So very low fraction of molecules possessing most probability velocity. I mean, in this particular time, maybe 40 molecules are possessing this velocity. But when temperature increases, see this curve. Under this area, more number of molecules are present. Then here maybe 65 molecules are having most probable velocity. So you can apply same condition to the students. When without teacher, they are not studying. But when any in charge comes and if in case he shouted on students, maybe the graph shifted to right side. Maybe some students they'll try to study, and some students who are not studying, maybe they're trying to study. Then most of the students who are not studying, they're trying to study. Are you getting my point? So this is simply called theory of probability, or simply Maxwell-Boltzmann distribution curves. So my point is, getting graphs are not important. They got graphs in different way. We don't know that. But we are studying graphical, these graphs. How can we understand theory from these graphs? Even if you increase the temperature more than T2, the graph move further into the right side, and it becomes flatter, flatter, flatter. Are you getting? So when temperature increases, most of the molecules are having most probable velocity. Hello students, did you understand this concept? What is Maxwell-Boltzmann distribution curves? Yes. So it's a very good concept, and very important for advance, particularly advance. Try to understand student this one. In tomorrow class, I'll give complete notes on Maxwell Boltzmann. In case if you have any source, try to get information about Maxwell Boltzmann distribution curves. Okay. So even in physics also, you may study in physics. I mean, you will study definitely in physics also, but in chemistry students, just we have this kind of method of studying. We don't have any equation based distribution curves. So we don't need that equation. Try to understand this. We don't need equation, but we need these graphs. Yes, definitely these graphs are very important. We should draw this in examination. In case if you get, you have to draw this. Okay. But in tomorrow class again, I will explain. But I think most of the students understood this concept, right? Yes, very easy, Nana. Just apply this concept to our normal, general concept like students or some other things. You can understand them. Okay, right. Okay, students. In tomorrow class, we'll study